In reading number 2 for comparative biomechanics, we're going to discuss another biomechanical marvel of the animal kingdom, and that is the kangaroo. This paper is titled Energetic Cost of Locomotion in Kangaroos by Dawson and Taylor, 1973. This paper was published in the journal Nature, which is probably the most prestigious academic journal in the world. And most of the publications in that journal are published in letter format. And so this is why most of the first column of this PDF is on some other paper. It's the end of the previous letter, and also why you don't see the names and affiliations of the authors here until down at the end, where normally we see the authors here up at the top of the paper. That's just kind of how they do things for a lot of publications in this journal. But here they were examining the energetic cost of locomotion in kangaroos. And what is a kangaroo exactly? I assume most of you are at least superficially familiar with a kangaroo. They are looking like this fellow right here. This is actually only one particular type of kangaroo. There's lots of different types of kangaroos and lots of different other species of animals classified under the general umbrella of marsupials that are kind of conceptually similar to kangaroos. But this is the guy that we usually think of when we hear the word kangaroo. This is specifically a red kangaroo, and these are, to my knowledge, the largest and fastest of the kangaroos in Australia. Kangaroos are found only in Australia, and there are a variety of them, but you only find them, as far as I know, in the continent/island of Australia. Kangaroos, of course, are well known for their mode of locomotion of hopping. They don't exclusively hop. They have other modes of locomotion, as we'll see another one beyond or other than hopping in the paper here. But that's certainly what we think of when we think of kangaroos. The kangaroos, and they're famous for their mode of hopping locomotion. They are, at least the red kangaroo, the one that we will study here, is, again, like the cheetah, is roughly similar to an adult human in size. The adult male red kangaroo can be over 6 feet tall and can weigh around 200 pounds or so. So a little bit bigger on average than your typical, like, healthy adult male, but again, still roughly comparable to an adult human in size. So we'll see here, like the cheetah, another animal that vastly outperforms human locomotion characteristics despite being roughly similar to an adult human in size and general shape. So this hopping mode of locomotion, they can do this really, really fast and really, really efficient. Here is a video I found on YouTube of a kangaroo hopping, and they're doing this while they're being filmed from a car traveling at normal car-type speeds on the road from which they're filming here. So watch the background just blur by here as the kangaroo is hopping along there. And I don't know how quickly he's hopping there exactly. Maybe they'll say it here in the video. I didn't actually watch all of this. But that is a pretty fast speed for that animal to be hopping along there. It's really keeping up with a car without too much trouble. These guys can reach, I don't know what their top speeds are, but they can sustain speeds of in excess of 20 miles per hour for like several minutes at a time. Like they can travel several miles on end without stopping and resting at those speeds, which are bordering on like an anaerobic effort, but still traveling at that speed for more than a few minutes at a time is something a kangaroo can do, and is going to be something that's primarily an aerobic effort in terms of the energy that they're consuming while they're doing that. So they can travel with this hopping mode of locomotion, can travel at really fast speeds with a really low energy expenditure. So that's one thing that's kind of unique about them. What's really a marvel in terms of the finding in this paper. The first marvel was that they did this study at all. If I was going to measure the metabolic energy expenditure of a human running on a treadmill, I would put you on a treadmill and I would hook you up to some equipment involving a mask and some tubes that connected to special machinery that connected to a computer that measured your rate of oxygen consumption and various other factors that I would need in terms of breath by breath data there that would allow me to estimate your metabolic energy expenditure from those data. So I'd hook you up to a treadmill and have you wear a mask that kind of tethered you to this computer that was measuring the things that I needed to do that. They did that here, but they did it in kangaroos. They trained two kangaroos, a larger adult male and I think a smaller adult female, to not only hop on a treadmill at a variety of speeds, but to do this while they were wearing the energy or the oxygen measuring mask while they were hopping on the treadmill. So I don't know what's involved in getting a kangaroo to actually do that, but they did indeed train kangaroos to do this. And this is some really unique data. At the time in 1973, this was for sure the first and only data on the energy cost of locomotion in kangaroos. And there may have been others since then, but this is certainly some really unique data for sure. So what did they find here that was so cool? It is shown here in figure 1, the only figure in the paper, and in the top panel of the paper here. You guys aren't going to be able to see the labels on the x-axis here, but the x-axis here is the speed of the treadmill while the kangaroos were traveling on it. The symbols here are the individual data points from the two different kangaroos while they moved on the treadmill at these different speeds. They found that at slow speeds on the left here, so to the left of this demarcation here, those were speeds ranging from like 1 up to about 6 kilometers per hour, which if I convert that to treadmill units that you guys are more used to, 1 kilometer per hour divided by 1.6 would be about 0.6 miles per hour on the treadmill, so hardly moving, and then 6 kilometers per hour would be about 3.7 miles per hour on the treadmill, which would be a pretty fast walk for a lot of people. Then they also measured speeds beyond that up to like 22 miles per hour, which would be 22 kilometers per hour, which would be about 14 miles per hour, and that's pretty darn fast. Most treadmills won't even go that fast. A lot of treadmills top out at like 10 to 12 miles per hour, which would be a 5-minute mile. So 13, 14 miles per hour is pretty darn fast pace on a treadmill for a human. So that's the range of speeds they were looking at here. What they found was that at speeds slower than about 6 kilometers per hour, the kangaroos there did what they referred to as a pentapedal gait. And what does that mean exactly? Pentapedal gait. Penta means 5. And what does that mean exactly for a pentapedal gait? Penta, meaning 5, means they have 5 points of ground contact, or 5 parts of the body that touch the ground when they're locomoting. Humans do bipedal locomotion, bi meaning 2, because we have 2 points of ground contact. We have our left foot and we have our right foot, and those are the parts of the body that touch the ground when we're doing our most of our modes of locomotion. The kangaroo here, they found at the slow speeds below about 6 kilometers per hour, did a pentapedal gait with 5 points of contact. So you've got the 2 hind limbs, that's 2 points, the big ones that they hop on. You've got the 2 forelimbs, the arm-looking kind of limbs of the kangaroo, that's 4. What's the 5th one? Where's this magical 5th point of contact coming from? That is the tail back here. Kangaroos have a fairly large and heavy tail that they also use for ground contact at slower locomotion speeds to support a little bit of the body weight. So I don't actually know what this gait looks like. I couldn't find a picture of it, or a movie of it. But they found at the slower speeds, the kangaroos here did a pentapedal gait, touching the ground with these 5 points of contact during their gait cycle. Each of the feet, each of the arms, and then also the tail here for those 5 points of contact. At those slow speeds, as you can see here, the faster that they did that pentapedal gait, the faster that they consumed oxygen, or the faster that they consumed the fuel that they needed to power their muscles to continue on the treadmill at that speed. On the y-axis here is the time rate of oxygen consumption, the milliliters of oxygen consumed per hour. And this is our typical way of quantifying how quickly the fuel that we use for locomotion here, at least for aerobic efforts, is being consumed. And this kind of linear increase, or just rough increase, in terms of how quickly we need to consume oxygen with how quickly we are transporting our bodies, is what you typically see in most animals as they travel at faster and faster speeds. But interestingly, what they saw here was that at around 6 kilometers per hour, when they tested them at speeds faster than 6 kilometers per hour, so up to like 8 kilometers per hour or faster here, there they saw that the kangaroo transitioned to a hopping gait, so hopping bipedally on both legs there, like we saw in the movie for the kangaroo. And when they transitioned to that hopping gait, on average, the rate of oxygen consumption needed to power that gait decreased a little bit. And what's really remarkable here is that as they hopped faster and faster, on average, actually, their rate of oxygen consumption they needed to sustain that gait at that faster speed decreased. That is extremely remarkable and unusual, and I don't have an exhaustive knowledge of comparative biomechanics. There could be other animals that this is observed in certain gaits that could be out there. I don't really know for sure. This is certainly the only animal that I personally know of where this has been observed, where they have a mode of locomotion where the faster they go, the slower they consume oxygen while they're performing that mode of locomotion. That's extremely unusual. It's unheard of in humans. In humans, our sensitivity of the rate of oxygen consumption or rate of metabolic energy consumption as we increase speed looks like this. For walking, as we walk at faster and faster speeds, it's this kind of curvilinear or kind of quadratic relationship, where again we're consuming oxygen at a faster rate as we walk faster and faster. And for running in the orange, we also see that same thing. It's more of a linear relationship compared to this curvier relationship in walking. But for running, we see qualitatively the same thing. Whereas you run faster and faster, you consume metabolic energy and supply oxygen to your muscles at a faster and faster rate to sustain that faster and faster speed. This is what we think, or at least what a lot of people think, what we are sensing in terms of effort when we run on a treadmill or when we walk on a treadmill at faster and faster speeds. And as we do that, our perceived exertion, the effort that we're putting out, increases. It feels harder and more difficult to travel at that speed. What we think that is that that's the sense of the body telling us, okay, I'm doing this, I can sustain this, but I can't do it forever. You know, you're going to be limited on time here in terms of how long you can sustain this effort here. So sensing the time rate of metabolic energy expenditure, the time rate of oxygen consumption there. So in humans and in most other animals, regardless of the mode of locomotion that they're using that I'm aware of, generally the faster you go, the faster you consume fuel, the faster you expend metabolic energy to sustain those faster speeds. That is not what we saw here in the kangaroos when they were hopping. We actually saw the opposite of that. On average, the faster they hopped, the less rate or the slower the rate of oxygen consumption they needed. So imagine like being on the highway, and the faster you drive your car, the slower it consumes the gas in the car per unit time. Okay, that's pretty much unheard of in an automobile, and it's certainly largely unheard of in biological animals. So this is a pretty remarkable finding here. What is it about the kangaroo that allowed it to do this? They don't really know for sure. There's been studies that followed this up in the preceding, or the like 40 years that have occurred in comparative biomechanics that followed this study. As far as I know, it's still not definitively confirmed what the kind of mechanical or muscular source of this remarkable phenomenon is here. What they speculate here, and what I think is still the leading theory on where this comes from, is a particular part of the kangaroo's body, their Achilles tendon. We saw in humans that the Achilles tendon is one of the largest and strongest, probably the largest and strongest tendon in the body, and it probably stores and returns a great deal of strain energy and returns it as kinetic energy. And if we can do that, then this could theoretically be a source of energy savings or a source of economy in human locomotion, such as running. In the kangaroo, check out this guy's Achilles tendon. It is this giant piece of tendon right here. They have an absolute steel cable of an Achilles tendon. It is extremely long and extremely thick and extremely strong. And so when you stretch that tendon, even by a little bit, it's going to store a great deal of elastic strain energy in it, and through that be able to return a great deal of energy as kinetic energy, ideally supporting the body and helping to propel it forward. So the theory here is that as they hop along at those tremendous speeds with their whole weight supported on just these two limbs here, that involves a lot of force under the legs, involves a lot of force in the muscles, which results in a lot of force applied to this tendon, a lot of stretch of that tendon, a lot of elastic energy stored in that tendon, and then more energy returned as kinetic energy to kind of help the animal locomote economically there. At least that's the theory at the time, and I believe still the leading theory today on how they're able to do this, by having not just a large and strong Achilles tendon, but an exceptionally, remarkably large and strong Achilles tendon, far beyond what a human Achilles tendon would be capable of here. Last interesting point that they make here in this paper is this last paragraph. And remember that I said early on that these animals, these kangaroos, are only found in Australia. You don't see them anywhere else in the world. This feature that they have in their locomotion, this phenomena where the faster they hop, the more economical they get, or the slower they consume oxygen to hop at faster and faster speeds. For an animal like this, which is a herbivore, which is probably going to be chased by other carnivores trying to eat it, this would seem to be a really advantageous, really helpful, beneficial thing. Okay? If you are trying to flee, for example, from a predator, if you can do that at speeds in excess of 20-25 miles per hour, and can do that pretty easily with like largely aerobic type efforts and can do that repeatedly throughout the day, that would seem to be a really beneficial thing. Unless something really, really fast is chasing you, you're probably going to be able to get away. And if you're a kangaroo like this, you're a pretty large, strong animal, your number of predators is probably pretty limited. It's not like just anything can chase you down and can actually damage you and hurt you if it manages to catch you. So being such a big animal that is able to travel at such fast speeds with such economy, and even more so traveling at even more economical rates of energy expenditure the faster you go, this would seem to be a remarkably beneficial adaptation. So why is this so rare? Why is it only this particular mode of locomotion for this particular animal found only in this one place in the world? Why is that the only place we see this? Shouldn't we be seeing this all around the world if this is such a beneficial thing? I don't really know why that's the case. I don't think anyone really knows why that's the case. They make some suggestions here on why that may have happened, but again, this is another thing, to my knowledge, where we're still working on it. We don't really know what the definitive source of this is, or why it's so rare, why it's only found in this mode of locomotion of this one particular animal for the most part. So one of the mysteries here of comparative biomechanics that hopefully will get sorted out by research in the future. Okay, that is it for today. We will see you next time.